Okay, so we are now firmly into chapter 17, and we are looking at differentiated rate law. So here's an example of a typical problem that we're going to be looking for. And it says write the rate law for the reaction and find the value in units of the specific rate constant. So I put it over here so I'd have some room in the bottom to work so you could see better what I was doing. And let's jump right in and see what happens. So what we're trying to find here when we're writing a rate law is we are going to try to find the value of the rate constant K and the order of whatever reactant or reactants we have. We only have one reactant. This is dinitrogen pentoxide, and we have three reactions here. So what we're going to do is we're going to try to assess the relationship between changing concentration and rate. So we have three experiments here. Now, if this was a situation where we had multiple reactants, we'd have to choose our experiments carefully, but we don't need to do that here. So I'm just going to stick with experiments 1 and 2. And the first thing I'm going to try to do is I'm going to try to find the order. So the first part is determining the order, the order of N2O5. We want to find this value N. So I'm going to take these two experiments. Let me make this a little smaller. I'm going to pick experiment 2. I usually put the bigger one on the top. In experiment 2, we have a rate of 4.4 times 10 to the minus 2 moles per liter seconds. This is equal to a rate constant K that we don't know. And the concentration of N2O5 is 0.04 moles per liter raised to some power N that we don't know. I'm going to compare it to experiment 1. In experiment 1, we have a rate of 2.2 times 10 to the minus 2 moles per liter per second, equal to a rate constant K, which we don't know, and the concentration is 0.02 moles per liter raised to some power N that we don't know. So what we're going to do is we're going to turn these into a proportionality, in a manner of speaking. So we're going to turn these into an equation. We're going to cancel out the things that we know to be the same. In this case, the only thing that's really the same is K. And obviously, all these units cancel out too, and we're not really worried about that, but we'll get to that in a bit. So since we're going to leave all these units in, let's bust out our calculator. I don't think you need one for this, but just to be thorough, we'll say, let's put this over here so I'm not blocking my numbers. 4.4 times 10 to the negative 2, and we're going to divide that by 2.2. Whoops. A little clunky. 2.2 times 10 to the negative 2. It's really not necessary, but we'll do it anyway. So over here we have 2 is equal to, and we're canceling all this stuff out, and what we're left is with 0.04 divided by 0.02. You do not need a calculator for that one. It tells us that the order is 1, because 2 raised to the first power is 1. And that means that this is a reactant that is what we're going to say first order. So if we were going to describe this reactant, we would say that the reactant is first order, or that the experiment is first order in N2O5. All right, now that we know that, let's find K. So what we're going to do is we're going to pick an experiment. We're going to plug all this stuff in. We're going to solve for K. So I'm going to take experiment 3. We've been kind of neglecting it. So we'll take experiment 3, and I'll pop this over here. That's not what I wanted. We'll put experiment 3 over here. And what we want to do is we're going to solve for K. So what we know is that rate is equal to K times the initial concentration of N2O5 raised to the N, where we know N is equal to 1. So let's plug this stuff in. For experiment 3, we have a rate 6.6 times 10 to the negative 2 moles per liter per second. We're trying to solve for K, and we have an initial concentration of 0.06 moles per liter raised to the first power, which we don't even need. All right, so let's first take care of the exponent. When we do that, we have 6.6 times 10 to the minus 2 moles per liter per second equals K times 0.06 moles per liter, because that's what happens when you raise everything to the first power. And now we're going to solve for K. We're going to do that by dividing both sides by 0.06 moles per liter, and this is going to give us K. So we'll get the value, and I don't think you need a calculator for this one either, but we'll do it anyway. We'll say 6.6 times 10 to the negative 2 divided by 0.06 gives us 1.1. So our value for constant K is 1.1, and look what happens to our units. Moles cancels moles. Liters cancels liters. It leaves us with seconds in the denominator. And that can be tricky to write, but we're just going to say that we are using the inverse of seconds. There you go, ladies and gentlemen. The answer to question number 1. The order is 1. And the value and units of the rate constant K is 1.1 seconds to the negative 1. All right? That's all we're doing. So let's take a look at number 2. I've put it down here, moved it over a bit. All right. Oh, look at this. Something interesting is going on. We have one reactant. And look what happens. When we double the concentration from 0.035 to 0.07, the rate goes from 4.5 times 10 to the negative 2 to 4.5 times 10 to the negative 2. Look at that. In other words, changing the concentration of NH3 at the beginning of the reaction has no effect on the rate. Well, what does this mean? Well, let's try this out and see what happens. So let's pick a couple of experiments. And we can do 3 and 2 if we want to. It doesn't even matter. So I'm going to take experiment 3. We're going to try to write the rate law for this. Before we even get to experiment 3, the rate law is going to look like this. Rate is equal to some rate constant K that we don't know times the initial concentration of ammonia. And we want to find the value in units of the specific rate constant. So I'm going to take experiment 3, which we have a rate of 4.5 times 10 to the minus 2 moles per liter per second. And this is equal to a rate constant K that we don't know. And in experiment 3, the concentration is 0.105 moles per liter raised to some power that we don't know. Let's compare this to experiment 2. In experiment 2, we have 4.5 times 10 to the minus 2 moles per liter per second is equal to some rate constant K that we don't know. And in experiment 2, the initial concentration is 0.07 moles per liter raised to some N that we don't know. So typically what we do is we're going to turn these into proportionality. And I don't think you need a calculator for this first part, because 4.5 times 10 to the minus 2 divided by itself is, of course, 1. Well, we don't know k, so we're just going to get rid of it because we know it's a constant. And so let's take this 0.105 divided by 0.07 and see what we get. So we're going to say 0.105 divided by 0.07, and we get 1.5 raised to the n is equal to 1. Ladies and gentlemen, anytime we raise some value to some exponent, and the answer is 1, the exponent must be, anyone want to guess? 0. And that means that the value for n is 0, what we call a zero order reaction. Because as we've said, changing the concentration has no effect on the rate. So n has to be 0. Now, if we'd seen that before, we could have gotten the value for the order without even setting this up, because we can see here that changing the concentration has no effect on the rate. So the order is 0. Let's get the units, the value in units of the rate constant k. So we'll pick experiment 1, and we'll do a little snip. So we'll get experiment 1, and we're going to find the value in units of the rate constant k. So let's put this down here so we don't have to look for it. All right, so we want to find k. So in experiment 1, we have a rate of 4.5 times 10 to the minus 2 moles per liter per second. So there's some rate constant k that we don't know. And the concentration of NH3 at the beginning is 0.035 moles per liter raised to the n. Ladies and gentlemen, when you raise anything to the exponent and the answer is 1, the exponent must be 0. What that means is that any value raised to an exponent of 0 is always 1. Ladies and gentlemen, that means we don't have to go any further. 4.5 times 10 to the minus 2 moles per liter per second equals k times 0.035 moles per liter raised to the 0 is now just k. And that means that k is our rate constant with a value of 4.5 times 10 to the minus 2 moles per liter per second. Or you could say that because this reaction is 0 order, the rate itself is constant. And there you go.